Hello. In this video, I'm going to explain problem 14 from the 2013 F equals MA exam. In this problem, we have a cart of mass m moving at 12 meters per second to the right, and it will collide elastically with a cart of mass 4 kilograms that is originally at rest. And after the collision, the cart of mass m moves to the left with a velocity of 6 meters per second, so I'll write that as -6. And the mass of 4, we're not told, so it'll move, suppose at some speed v. So here, we have two variables, m and v. So one thing is that for convenience, I'm going to just assume SI units and then basically just drop the units. So everything, so m is in kilograms, and then v is in meters per second. And from now on, I'm going to drop the units and just work with them as numbers, because that tends to be easier in problems like this. So, and we're asked, what is the velocity of the center of mass of the two carts before the collision? Now notice that the velocity of the center of mass is just the total momentum divided by the total mass. And by the conservation of momentum, this stays the same before and after the collision. So really, when they say before the collision, that doesn't really matter. We're basically asking for the velocity of the center of mass of the system before or after the collision. So now, let us set up our equations. So our first equation will be the conservation of momentum. So we have m times 12 plus 4 times 0 equals m times -6 plus 4 times v. That's conservation of momentum. Then, for elastic collisions, this is something that deserves explaining in a video of its own, but there's an equation which basically states that the relative velocities, or the relative velocity of one object relative to the other, stays the same in magnitude but changes sign. You'll also see this sometimes written as that the velocity of approach, so the velocity, the speed at which one object approaches the other before the collision, equals the velocity of recession, so the speed at which the object will move away from the other after the collision. Oh, sorry, not approach, recession. So the speed at which the objects move away from each other after the collision. And so what is the velocity of approach at first? That just equals 12. And the speed after the collision will equal, so, well, at first, let me just be explicit about it. The velocity of approach will be 12 minus 0. And after the collision, the velocity of recession will be v minus -6. Now from this, we can immediately see that v has to equal 6, and then we can compute that m times 12. So we can move the m times -6 to the other side, so it will be m times 18 equals 4 times 6. And then we will get m equals 24 over 18, which is 4/3. And so, now what is the velocity of the center of mass before the collision, or at any time really? That will be the total momentum divided by the total mass. And so that will be the total momentum. We can just calculate that before the collision, so it will be 4/3 times 12 divided by the total mass. It will be 4/3 plus 4. And so that is equal to 48 over 3, which is 16, divided by 16/3. So that will be 3, and since we were working all in SI units, it's 3 meters per second. Now, there's actually another very beautiful way to get this answer. So the heart of the idea is that equation that I mentioned earlier, velocity of approach equals velocity of recession, but the key is to look in the center of mass frame. So what happens in the center of mass frame? And in fact, this is one way to see why the velocity of approach equals velocity of recession is true in general. So as I have m1 and m2, and what will happen is that they will move, so I'm going to write p1 and p2, so these are not the velocities, these are the momenta. In the center of mass frame, the total momentum is 0, and so p1 equals negative p2, right? And then afterward, the objects are going to move away from each other. But of course, since momentum is conserved, the total momentum has to be 0. However, we know that the kinetic energy has to be conserved as well, because we are told that the collision is elastic. And so the only way for that to happen, especially if, so let's say this momentum is p1 prime, this momentum is p2 prime, we have, again, p1 prime plus p2 prime is 0, but we also have that the kinetic energy before in this frame, which is p1 squared over 2m plus p2 squared over 2m1 and then 2m2 will equal p1 prime squared over 2m1 plus p2 prime squared over 2m2. And the only way for these equations to be satisfied is basically to just have p1, or p1 prime equal to negative p1, and p2 prime equal to negative p2. So basically, in this center of mass frame of reference, the momenta of the two objects just stay the same but change signs. And so this ultimately means that the velocity of approach does equal the velocity of recession. But now what can we see from this? Well, we know that the velocity of the mass, so we remember we had a mass m, then we had a mass 4 kilograms, and if we look at the center of mass frame of reference, we don't know what it is yet, because we're literally asked to find the speed of the center of mass, but we know that the center of mass frame of reference will be the one in which the velocity will literally just change signs. This is before, and then it'll be negative v afterward. But we know that in our original frame of reference, we have 12 meters per second to the right, and then 6 meters per second to the left, and so that's really negative 6. And so the question is, in what frame of reference will the two velocities actually be equal in magnitude but opposite in sign? And some relatively easy calculation. So if we want to know the center of mass frame, it'll be 12 minus VCM equals negative 6 minus VCM. Because this will be the velocity before. The left-hand side is the velocity before in the frame of reference of the center of mass, and the right-hand side, without the initial minus sign, is the velocity after the collision. And so if you compute this, 12 minus VCM is 6 plus VCM, and we'll get 2 VCM is 6, and so VCM is 3. And so this is a way of seeing that the velocity of the center of mass is 3 meters per second. And notice that in this derivation, we only looked at the fact that the block of mass m changes the sign of its velocity in the center of mass frame of reference. We actually did not use, so I'll just write this here, did not use m or v. And so in fact, it actually doesn't even depend. We computed m and v in this system, but the answer actually does not even, to find the answer, you actually don't even need to compute m and v at all. And really, it also means that the fact that the block of mass 4, the fact that it started at rest, and really, so to be more specific, two important facts: the mass of this block and the fact that this right block of mass 4 of known mass started at rest actually don't matter. And so this is a particularly beautiful way of solving this problem, which really goes back to the heart of why that formula, velocity of approach equals velocity of recession, is even true. And I think this is an example of why it's often good to not just know a theorem, but also to know why it's true. Because sometimes if you go back to the more fundamental principles of why that theorem is true, one, you achieve a deeper understanding, and two, you can find results that are very beautiful without just blindly applying the theorem. So I hope that was helpful, and thank you for watching.